Good evening and welcome. I'm David Nuremberg, and today I have the delightful task, not exactly of introducing Tadashi Tokieda, but of introducing his introducer. I will speak a little bit about Tadashi Tokieda, whose professions, or perhaps I should call them passions, because he brings passion to everything he does, have ranged from, well, across all of the arts and sciences, from painter to classical philologist to literary, not exactly scholar. It's about the passion. It's about. Well, I don't know how to describe someone capable of conversing about romantic poetry from Europe to China to the Arabs and back. To professor of mathematics at Stanford. Earlier today, we also saw him revealed as something of a mage, or maybe a natural magician, something akin to the natural philosophers of the ancient world in his ability to produce both wonder and knowledge simultaneously, but with a much greater sense of fun than any ancient, well, maybe not than any, but most ancient natural philosophers. And those of you who experienced his Adler lecture yesterday will know that he has an uncanny ability to bring together aspects of the physical and the mathematical worlds in ways that transform both and yield a sense of marvel. His lecture yesterday offered numerous examples. I'll just mention a couple. A new proof, and there are many proofs known, for the inequality between the arithmetic mean and the geometric mean, interpreting the means as final and initial values of entropy, and the inequality as the second law of thermodynamics. To give you a sense of the flavor, he began with high school science. Even I could understand. Imagine bodies of mass M1, M2, etc., having the same specific heat, C. Recall that specific heat is the amount of heat needed to raise the temperature by 1 degree of a unit of mass of that material and is measured in joules. So in other words, beginning with something from the physical world that we all know, a few translations back and forth between the physical and the mathematical worlds, and hey presto, a new mathematical proof emerged from his hat. Yesterday he did this over and over again, offering, for example, a viscosity proof of the Cauchy-Schwarz inequality for positive quadratic forms, interpreting the quadratic form as kinetic energy and the inequality as dissipation in a viscous flow. Each time, the result was a new sense of wonder about the world, and the audience broke into spontaneous applause after several of these magical QEDs, just as they did actually earlier today at the magic, can I call it a magic show? I never thought I would quote Nietzsche to introduce a mathematician. But while learning from Tadashi at his Adler lectures, I was reminded of the philosopher's complaint that what most of the world wants when it asks for knowledge is, quote, that something strange should be reduced to something familiar. For Nietzsche, the greater discovery lay in rendering the familiar strange. This is, it seems to me, precisely what Tadashi does. He's also widely known for his work with toys, toys as in quotation marks, taking objects we think we know and defamiliarizing them into puzzling items which help us to perceive astonishing aspects of our world. That is in some ways, if you ask me, a beautiful metaphor for what we do here at the Institute. So I cannot wait to experience the surprise that awaits us tonight. But first, a word from someone who can speak more magically and certainly more knowledgeably about Tadashi Tokieda than as a mathematician than I can. Please welcome my colleague from the School of Mathematics, Camilo de Lelis.
Welcome, everybody. So it's a privilege to introduce Tadashi Tokieda, a mathematician and a spectacular lecturer. I mean, not by mathematician standards, because that would be easy, but by the standards actually normal human beings. And I mean, at the end of the lecture, just remember the following. If you liked it, I am actually the guy who had the idea of inviting him. If you don't like the lecture, it was an idea of the School of Mathematics that I'm actually humbly representing over here. So our wonderful director already alluded to some of, to the unusual path to mathematics that Tadashi had. So he mentioned painting, although just mentioning it doesn't quite give you the idea, because you have to know that a major art gallery in Tokyo held an exhibit of his artwork. And that still doesn't give you an idea, because an important information is missing. When that happened, Tadashi was actually 5 years old. So he later became a philologist, and he started a university career as a philologist. And as it happens to actually many of us, then he fell in love with mathematics in a way that I'm not going to describe to you. It's weird even for the standards of math departments. So I strongly encourage you to Google this, because there's an interview on Quanta magazine in which he's actually describing how that happened. Anyway, that happened, and he got a PhD here at Princeton University under the direction of William Browder, and then he started his career as a professional mathematician, which, by the way, every mathematician knows it's an oxymoron, because mathematics is mostly a hobby. So anyhow, so he went to the University of Illinois Urbana-Champaign, and then he was in Cambridge, and finally, as it was actually mentioned by David, he became professor at Stanford, where he is now. And so let me talk a little bit about the mathematics. He started out as a symplectic topologist. Now, I know some of you are actually asking themselves, what the hell is that? I can't answer you, because I don't know it myself, actually, but luckily, one of the people in this audience is one of the father founders of symplectic topology, and if you're interested in it, it's very easy to spot him. He's actually the tallest guy around. He then got more interested in problems which have to do with mathematical physics, like the application of mathematics to physics, so like the locomotion in viscous fluids, or the dynamics of vortices, again in fluids. But the most astonishing thing was actually already pointed out by David. So yesterday we witnessed a lecture in which he actually proposed a sort of reversal. So we're used to think about mathematics as something that you can, successfully apply to physics. He actually advocated that you should try, and we should try, all of us, to apply physics to mathematics. It's not a completely new idea, right? I mean, because there have been wonderful discoveries which came actually from physicists who told us, like, mathematicians, what we should look at, and, how we should look at certain things. But, it's a very radical proposition, what he gave yesterday, because as it was mentioned by David, he actually managed to give a proof of Pythagoras' theorem using gas dynamics. So I was wondering whether, he's starting a completely new subject, which, I mean, if you call the application of mathematics to physics, mathematical physics, so he's a mathematical physicist. But if you reverse that, so he must be a physical mathematician. So here, I actually leave the floor to Tadashi Tokieda, physical mathematician and spectacular lecturer.
Would you like to see a magic trick? Two large coins and one small coin, quarters and a penny. If I put the large coin underneath and the small coin on top, so small one on top and large one at the bottom, and drop them, they drop in order. Of course they drop in order, top one on top and large one at the bottom. But now, make a sandwich, a tight sandwich of the small coin between the two large coins, and presently I shall release only the two bottom ones, an open sandwich as it were, while keeping the top coin between my fingers. Okay, like so. I don't know if you can see, and like so. And I'll try to do that a little better. Yes. So what you are going to see is this. Yes, and then I can try to drop them as horizontally as humanly possible. I'll try to do that again. They flip over in space. So the top became the bottom, and bottom became the top. And of course, you can try to make them flip over on purpose, but it's not the point. The point is that even if I try to drop them in order, they drop over and flip over. So what is going on? Oops, why is, oops, I can't see her. Sorry, okay, good. So you drop, and next time you just make a sandwich between the two large coins of the small one, and then it flips over. So there are many theories that have been proposed. One of them is that it has to do with the effect of the viscosity of the air that rushes in as you. But actually, it doesn't really work. Back of the envelope estimate shows that it's really insignificant. And besides, the sandwich is not that tight. I mean, there's plenty of room for the air to go in and out. So that doesn't work. Well, a way of finding the center of gravity of any object, not necessarily a uniform one, for example, such as this. Yeah? How do you do this? Well, you can guess. It's not really in the geometric middle because there's more mass here than here. So maybe it's somewhere here. But the way to do it is to put fingers underneath and then simply to draw the fingers together toward each other. And automatically, they converge to the center of gravity. In fact, it's so easy that I can close my eyes and look the other way, and then it automatically finds the center of gravity. And you see it's balancing there. Okay. So how does this work? It works because one of the fingers initially is closer to the center of gravity, and that finger carries more weight. That means more friction. So the finger that starts sliding is the finger that is farther away, that has less friction. And it comes closer and closer. But when it overshoots, then the other finger becomes the less frictional finger, and then you get an oscillatory convergence to the center of gravity. Okay? And this is really what is going on in this case. Now, what happens if you reverse the process? That is, you start from the center of gravity and pull the fingers apart. Well, you might think naively that, well, I can start to do gradually, little by little, until the fingers reach the ends and then they exit. But actually, that's not what happens. In fact, what happens is that when you start moving the fingers apart, one of the fingers starts moving aside, and actually the other finger doesn't move at all, and then at the end, the whole thing pivots. However clever you are, you cannot actually do one at a time and then pull both fingers apart. One of the fingers runs away and causes a one-sided divergence. And at the end, the whole thing pivots. Why is this? Because once a finger starts sliding, that finger becomes the less frictional finger. And so it has even more incentive to slide, even more incentive to slip, and then it just goes away, while the other finger, which is carrying all the weight, has to get stuck there. Yeah? So the reversal of this very familiar way of finding the center of gravity shows that however clever you are, you want to pull away two fingers at the same time, you cannot. And exactly this is what's happening. You see, when you do this experiment, you might think that, well, you can pull the two fingers apart and to release the bottom, the open sandwich. But in actual fact, what's happening is this in miniature under microscope. So one of the fingers leaves and the other finger being stuck. The whole thing pivots. And that is the dramatic flip over. You see, many people say that, well, there's a flip over because, of course, you cannot release the two fingers at the same time. There's an initial error. But, of course, any physical phenomenon has many, many initial errors. It's a redundant initial. That's not the point, because if there's only a small initial error, in the course of this falling, initial error will stay small. It will grow only linearly or something like that. The main question is, how do you find the instability mechanism which takes a small initial error and explodes it into something dramatic like a flip over? And this is the instability mechanism that we have successfully discovered. Okay? That's what it is. So it's a reversal of this familiar process. There are many mechanisms of dissipation, but broadly speaking, there are 2 or 3 mechanisms of dissipation. And dissipation is the friction, if you like, or wastage of energy, and something that you want to avoid. But one of the key features of this talk is that you want to know that some of the dissipative mechanisms actually are creative forces in nature and human society. So when the two bodies are rubbing against each other, this is a lateral dissipation, lateral friction, then there are 2 scenarios. Either you are rubbing together fluid against fluid or fluid against solid. That's one. So it involves a fluid. Then the theory is well understood. This is viscous fluid mechanics and so forth, that drag force, that kind of resisted rubbing, depends on how slow or fast you are rubbing against each other. And nature, of course, has to overcome this drag when moving through fluid. After all, we too are living at the bottom of the ocean of atmosphere, so we have to do this too. But also, biological nature is very, very shrewd in taking advantage of this apparent handicap in order to advance. On the other hand, when you have solid against solid that are rubbing against each other, there's the rub, as they say. So here is the first folio of Shakespeare's collected works, and that was published almost exactly 300 years ago, 1623. And the Hamlet in Act 3, Scene 1, as you recall, where is it? Has this to say. It's a funny spelling. I don't know if you can see it. It's the third line from the top. Perchance to dream, there's the rub. Yeah? And that I is spelled by a single letter I. It's quite interesting, isn't it, the spelling? Anyway, that's what it was. Okay, so we shall, excuse me, so I'm going to escape and then view screen mode. Oops, yeah. So solid against solid is very, very strange. First of all, there is some kind of drag force that resists the sliding, but that has to do only with how hard or gently the two bodies are being pressed against each other. It does not depend on the sliding speed, the slipping speed. So even if you are sliding very fast or very, very slowly, it's exactly the same friction. Very bizarre. But also, there's something else, which is that between not slipping at all, that's the sticking, and sliding ever so slightly, there is a big difference. There's a discontinuity, and we're talking about the static friction, which I'm going to denote by mu of stat, and then dynamic friction, mu of din, and one is greater than the other, typically by 20%, maybe 15%, that kind of thing. So it's very strange. There's a discontinuity in a physical experiment, and then there is dependence on the pressure, but not on the sliding velocity. And this opens a nest of worms, Pandora's box, because some of the rubs of solid against solid friction. For example, it's true that static friction is greater than dynamic friction, but imagine you take a table like this. How much force do I have to apply in order to pull this table, dislodge this table? Well, the answer, if you imagine a rigid table, so it doesn't deform at all, it's strictly rigid, then, of course, you have weight W, and you have to overcome that weight with the coefficient mu stat. So in the front legs, you have half of the weight. In the back legs, hind legs, you have half of the weight. So mu stat and W over 2 plus mu stat W over 2, that is the answer. Let's call this answer number 0, answer number 0. On the other hand, there is no such thing as a strictly rigid body. Anything has some elasticity, flabiness. Yes? So let's imagine some elasticity. Well, that's interesting because elasticity means that first I have to dislodge the front leg, but by the time I dislodge the hind legs, the front legs are already sliding, slipping. That means that I can overcome not the sum of those two things that I had before, but mu dynamic friction times half the weight plus mu static of half the weight. And because the static friction is greater, measurably greater than the dynamic friction, this answer epsilon, however small the elasticity epsilon is independent of the tininess of the elasticity epsilon that you introduced. Completely independent, because it doesn't matter what speed you're sliding at. But this is very strange, which means that, you see, if you take the limit of the answer epsilon, as epsilon goes to 0, you don't get the answer 0. There's a discontinuity, and this is one of the sort of the great banes or excitements of mathematics applied to physics. This is called a case of singular perturbation. You cannot take the limit of something and recover what is the 0 case. There are more troubles, the rubs of this thing. Let's say you have this tube which is connected to a rod, and then there is a bulb at the bottom which is sliding on the floor, and then this tube goes up along a bar, which is slightly slanted. Well, in the beginning, the rod is very, very shallowly angled, but at some moment when the rod becomes quite steep, there is jamming, and no amount of sort of trying to push the rod up the bar will make the ball budge. In fact, if you keep doing that, the rod will break and the whole thing will collapse. That is quite remarkable because there is something called a critical sort of cone of friction, and this is an example of finite time singularity, a very, very simple system, but if you start doing classical mechanics, classical physics, as you go, extremely simple, the solution jams, and there's nothing beyond. Finite time singularity. Okay. Here is something that has been annoying me throughout my life since childhood. You know, I sometimes carry a long and thin object like this, and don't you carry this every day in your bag? And anyways, I carry this in my bag. And of course, the simplest way for this object to fit in my bag is to be vertical one, because it doesn't push against anything, and everyone is happy. But to know this object insists on fitting horizontally, and it's very difficult. I mean, if you try to move, you have to squeeze it in, and then really stresses the bag until the bag tears or the object snaps. What possesses the devil to do this? But anyway, this is part of the picture. And finally, another really great difficulty of the friction is that unbeknownst to lots of people, this empirical law of friction, which harks back to Coulomb of electrostatic fame, and then is used everywhere in engineering because it's so useful and so accurate, is actually incompatible with Newtonian mechanics, or to be precise, determinism thereof. How? You can set up a system like this. So there's a horizontal bar, and again, the tube which is sliding, and there's some friction, mu, and then a rod, and then a pendulum, if you like, hanging. And of course, you can launch this in various ways, and you just launch, and it slides back and forth while it's oscillating and so on. But it turns out that this system, which you can actually set up in a laboratory, there are plenty of initial conditions from which you can launch, for which the solution does not exist, or the solution is not unique. Finito for the determinism. And if you want to know, you can rig the coefficient of friction mu large enough so that this strange expression, so I'm assuming that theta 0, that the angle, is neither 0 nor pi over 2, okay? No. But anyway, you can do this. And if you do that, it turns out that if you push it in the positive direction, in that direction, then the solution does not exist, and negative direction, solution is not unique. So you can actually write it down. Yeah? The existence theorem is violated, and so is the uniqueness theorem. Okay, so with those troubles in mind, we shall nonetheless explore what friction and displacement in general can do. Who in this auditorium has heard of Columbus's egg story? It's very curious. In Japan, every child hears this story, but in the US itself, so the story is that when Columbus came back from the New World, the Spaniards who funded his journey held a banquet in his honor, and during which some of the mischievous nobles mocked him, saying, well, of course there was some continent to the west, so if you kept going, you were bound to reach it, and so what's the big deal? It was very easy. And Columbus said, well, they were having boiled eggs, as one does at the banquet, and he said, well, which one of you can make a boiled egg stand up on its end like this? And they all tried, and of course, the egg starts falling down, or of course, always falls down. And so they can't do it. And finally, Columbus took his egg and crushed part of the shell and made the egg stand up. And people said, ah, that's easy. Columbus has a reply, well, it's easy once you have seen somebody else do it. But I have always been very dissatisfied with this story, because what's the deal with crushing an egg? That seems to be cheating. So I would like to say that, in fact, there was a much better way of making an egg stand up, and here's one. So here's my egg. You can do it with an actual boiled egg, so it even says EG in International Phonetic Alphabet. And by the way, do you know a way of distinguishing a boiled egg from a raw egg? You can just spin it. Boiled egg spins very nicely because it's a rigid body, but unboiled, a raw egg, has some liquid stuff sloshing about inside, so it doesn't want to spin. But it's quite interesting because even if you have a raw egg and you keep coaxing, it eventually starts spinning, and then you cannot stop it anymore. Or to be precise, once you can get a raw egg spinning, you catch it, and a moment later you release it and you resume spinning again. It's quite interesting, but that's neither here nor there. So here's what it is. So it's an egg. All you have to do is to take this and spin. Oops. And then it stands up. Now, there have been, again, many, many theories. I shall be quoting many theories. Thank you very much. It's very... Of course, but there have many theories about this, and you might have noticed that this egg is always standing up. An egg has a bluff end and a sharp end. It seems to be standing up always on the bluff end with the sharp end pointing up. So there was some controversy in the dynamical systems community trying to model this, and very, very complicated theories are developed why it stands up only on the bluff end with the pointy end upward. And there were many, many difficulties. And finally, I came along and identified the main difficulty why we haven't been able to prove that it stands up always on the bluff end. And the main difficulty is that it's not true. Actually, it can stand up upside down. Okay, so that's what it is. Okay, now, that's the answer. You spin, and then it stands up. But this is very interesting. By the way, if you want to do this at home, you boil the egg. Make sure you will boil it first. And then when you launch it, catch it with 2 hands and then pull them apart. Because with 1 hand, if you try to rotate it, you don't get enough spin. Okay. So in general, we are familiar with the principle, so the pseudo principle, that nature wants to be lazy. It wants to lie down. That's preferable to sitting up. And sitting up is preferable to standing up. But a principle of what you can call tippy top, because it tips over, is that a spinning body in frictional contact, so dissipative contact with the floor, has a tendency to raise its center of gravity as high as possible, not lower it. That's very strange. And here are some of the familiar members of the institute. And also, I haven't been changing this. I'm not. What is this? Okay, that's a switch. And so here are familiar members of the institute, and Pauli and Niels Bohr, who are fascinated by the tippy top, which is in Lund 54. So I would like to show you some more tippy tops. So here is a typical one of the tippy tops that they used. And when I spin it, you'll see that it pops upside down. That's very good. Huh? And upside down position is really stable, while it's the center of gravity up position is very stable while it's spinning. So when I hold it, it's really stable. Yeah. Until it starts losing its spin. And then it's still standing up very vigorously. But eventually you lose the spin. And then you start saying, I don't want to look like a mushroom anymore because I'm not spinning. I'd like to return to my static and more normal upward state and sit upside up. Yeah, so that's what happens. Okay. If you want to, this is the theory that you can develop. But the main part of this theory is this last line. You can actually estimate the tip over time. How do you tip over? And I just showed all this rigmarole in order to boast that I can do this. And my theory is the best of all. And then the final line, I'm going to copy there. If you give me the parameters, so what's the radius of this object? So this is exactly 20 centimeters. So I can say it's about 3 centimeters in diameter. So radius is 1.5 centimeters. What is the gravitational acceleration? It's about 10 meters per second, 980 centimeters per second. How about the frictional constant, coefficient? That is the hard one, but I'm going to show you how to estimate it. Here is a little animal, and it's made of wood. And I want to have the frictional constant coefficient between wood and glass. This is very difficult, and if you Google, you're not going to look it up very easily. But I can tilt this thing all the way until it starts sliding, and that critical slope of the height over the width, that slope is equal to the coefficient of friction, but that's the coefficient of static friction. The dynamic friction is a little less. So this is, let's say, 1/3. So dynamic friction is maybe 1/4 between those. So that's how you can estimate. And then finally, how many spins does it make? So I'm going to ask you to watch this. This is really a tricky one. So when I launch, it's spinning very fast, and then it stops. So how many turns per second is it making? Well, how do you know? Well, I do, because when it's spinning, it's all a blur. You cannot really track the motion over the top, right? That means that it's spinning at least 10 times a second, because if it's slower, I can probably see that I can track. On the other hand, when I spin, you can still hear this woo noise. In other words, it's not in the acoustic range. And if you can hear it, it's at least 100 hertz. And so this is really between 10 and 100 turns per second. How do you estimate the number between 10 and 100? You might think that you should take the average between 10 and 100, 10 plus 100 divided by 2, but that's the wrong one. Because in this business, what you are doing is not to add, but to multiply various numbers. Yeah? So the idea is that, oops, what is going on? Yeah, idea is that you have twice r times omega over mu g. By the way, that's dimensionally the only possible form, so you could have gotten that answer, except for the factor of 2. But anyway, so you are multiplying. So the average that you should have between 10 and 100 is not the additive average or arithmetic average, but the multiplicative or geometric average. In other words, you have to multiply 10 and 100 and take the square root. That's about 30. Yeah? The square root of 1,000 is about 30, so I'm going to adopt that. So the estimate is that 2r omega over mu g. By the way, you don't have to listen to any of this. I'm going to sort of start boasting in a moment, so I'll wake you up. So that's twice 1.5 times 2 pi times 30 divided by 1/4 of 1,000. And if you do a calculation, it's a little over 2 seconds. So let's see. 1 second is 0, 0, 0, 0, 0, 0. That's 1 second. 0, 0, 0, 0, 0, 0, 1, 2, a little. Exactly. Amazing. So it is exactly right. Yeah? And this is when I start boasting and you should wake up. And I can calculate this, with this model, I can calculate absolutely everything about the tippy top. So it seems, for example, while this is turning over, the point of contact with the flow is sort of going up along the surface of the top. So if you, for example, dirty the floor with some soot and so on, it will stain some curve on the surface of the top. And I can even calculate that kind of curve. So it is strange, curious coil on coil. So there's plenty of room to be complacent about this. But little do I know. Okay. But let's move on to something else. So far, we have been talking about up and down, sideways. Those are translational motions. But what I would like to do is to introduce a rotational motion. That's another part of the universe. So here is a little stick with a propeller stuck at the top. And then there are notches along the stick. And then I can rub this. And when I rub it, this is going to sort of make the whole thing vibrate up and down. Except for accidents, there is no reason why it should spin one way or the other. But if I channel my ancient Japanese energy, I'm coming from an old nobility, and I can make it spin this way, or I can make it spin this way. And you think I'm doing something, but in fact, I can even look out. So I'm going to ask somebody in the front row, for example, Professor Dring, to say reverse whenever you want me to reverse. Okay? I'm starting, and I'll look away. So, did it reverse? Is it reverse? Okay, reverse again. Reverse again. So I can do it at will. So many people think that this has to do with catching a resonance. Certainly there is some kind of effect, so you accidentally start going one way, and then you keep pumping energy. But that's not all. There is much more going on, because as you have witnessed, I can actually control the direction of the spin at will. Okay? So rubbing, of course, seems to shake the whole thing shaft upside down, up and down symmetrically, and yet I can make the propeller spin chirally, and here. Yeah? And the reason this happens, because you seem to be such a great and nice audience, I'm going to reveal the secret for free, usually at judgment, is that when I'm rubbing this, I'm actually holding the stick like this, and I'm touching with my finger one side, one flank of the stick like this, and the other flank is loose. It's not exaggerated as that. It's just a different pressure on either side. What the difference does that make? Well, without this touch, what the shaft does upon being rubbed is up and down, up and down, up and down, symmetric vibration. But if you put a cushion on one side, the downstroke is free, but the upstroke gets bounced off sideways, and it starts creating a slight cycle. And this cycle swirls the nail, and nail entrains, if you like, this hole, and which spins the propeller. And that's how you can reverse. Okay? So how you can get chirality, that comes from the Greek word heir, handedness, is the secret of this. Now is the time to reveal, for the Institute friends only, and sub rosa, a rather scandalous object. Okay, So here is another tippy top. Do you know what happens if I spin it this way? Oops, sorry. It stands upside down. Okay, that's a very nice tippy top. By the way, about 5 minutes ago, many of you have never seen a tippy top, so you think it was impossible. Now, you think that every top has to stand upside down. But anyway, that's upside down. So I spun it with my right hand. But you know what? I am ambisinister. So I'm unskillful with both hands. So I'm going to now launch it with the same initial angular velocity, but with the opposite sign in the other direction. And then, oops, sorry, I should, then the top tilts a little bit. Can you see? It's tilting, but it doesn't actually tilt any further. It's trying and trying, but it doesn't tip over. It keeps up. So you have in your presence, almost under your nose via the camera, the world's first chiral tippy top. A top which spans one direction is a tippy top, stands upside down, but the other direction it does not. This is the third time that I shall say there are many, many theories of tippy top out there. They are competing, and some of them are more complicated than others. Of course, my theory is the best because I can calculate absolutely everything of physical interest. But none of the theories of tippy top out there allows, never mind, begins to explain the existence of such an object, including mine. So that means that despite our impression that we understand tippy top very well, with that complicated formulas and so on, there's a ginormous gap in our understanding. We have actually no idea. We have to go back to square one. Yes? So this was discovered some while ago. I started actually writing up something, the way we all excuse why we don't write up our results and so forth. And I started actually writing something, but I was interrupted by this. So maybe in a few years' time. Okay, so more mechanisms of dissipation continued now. We talked about the lateral dissipation, but now something that feels even more innocent, which is the frontal dissipation. That is when two things collide, some of the energy is lost in heat because it bounces, but maybe less vigorously than it went in. So many, many examples. And where does the heat, so-called heat, go? Of course, it's molecular jiggling. And sometimes the molecules are so jiggling out inside that it ends up breaking the object. That happens too. So you have some ball which is going down, boom, 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 down the slope. Or if you drop a teapot, it shatters on a tile. Why? Because it doesn't, instead of bouncing up, it wants to keep its energy inside, and then the energy has nowhere to go, so it just shatters, and so forth and so forth. So this kind of frontal dissipation is mathematically innocent, though it is actually capable of producing many phenomenological surprises. To give you one example, I shall do now the kind of main clou du spectacle. Here is a cup, can you see? With a long, long chain that I put inside, and whose end is sort of hanging, from the rim, okay? And I'm holding it with my finger, but when I release my finger, the chain will start flowing down under its own weight. And so what you should see is what is around here, what happens. You'll see that when I release this chain, of course, gravity is pulling everything downward, but the chain spontaneously starts standing upward, although there seems to be no upward force anywhere that is capable of pulling the chain up. So here we go. What the? Anyway, so now you have to be patient with me. Now I shall put this back in the cup. And I have to do this very, very carefully because, you see, if you dunk a chain into a pile randomly, with a very high probability it gets entangled. Isn't that interesting? So that's another thing that you can study. But in the meantime, I'm going to do it very, very carefully so that it doesn't get entangled and ready for the next action. So it is very, very strange that the chain stands up and with an upward motion, whereas nothing seems to be pulling it downward. Okay, so there are many theories that have been produced about this. And some of them I shall visit. Okay, I'm about to be able to do this. Okay, thank you very much for your patience. I'm saying that to the chain, not to you. Okay. So you release, the chain starts flowing down, and then stands up like a fountain, although there seems to be no upward force. Some of the theories, one of the theories is that when the chain hits the ground, somehow some messenger travels upstream from the ground and then sort of makes the chain stand up, whatever that means. That does not hold water, as it were, because I made an experiment on a tall tower, tall enough so that it's taller than the length of the chain, and it doesn't come anywhere close to hitting the ground, and then yet the chain fountain was formed. So that's not true. Next theory is that somehow when the chain starts flowing out, the chain likes this very sharp corner that it has to make in order to go out of the cup, a hairpin bend. So it wants to draw a gentler curve, yeah? And so that's why it stands up. That is not really good either, in view of a forgotten 19th century theorem which says that if you have a chain which is flowing fast enough, actually it can flow in levitation along any shape whatsoever. I'm going to give an example, but before that, this is the proof that if you find some local balance and the tension against sort of centrifugal force, actually the radius of curvature or the geometry disappears. It's cancelled from both sides. So what is left behind is this boxed formula in the middle, that is the tension will balance rho, that is the mass divided by per unit length, times v squared. And if you check, both dimensions are correct. So this is independent of the curvature, that is the shape, which means that whatever geometry you have, it's capable of flowing. So here is a concrete example. Suppose that you have a loop chain, which is sort of hooked onto a spinning motor. And then while it's spinning, it assumes some shape, and then you go there, and then you dent the shape. And you think that, well, when you release your hand, it might go back or something like that. But no, it actually keeps flowing in that dented shape for quite a long time. Yeah, so it has, it just keeps there. And that's because it's going fast enough so that the gravity doesn't matter. By the way, how fast is fast? That's the inequality just before. You should have this sort of acceleration per unit length should be greater than the sort of external force per unit length. Okay. So the question is, what possesses the chain to rise? It's not either of those explanations. And here is how we should think about it. So suppose that you have some rod which is falling, like so, but at some tilted angle. And then when it hits the ground, what happens? Well, this thing bounces and instantaneously spins the whole thing. That means that if you look at this end and sort of the other end is invisible, you have the impression that as soon as you hear this bang, it started going down faster. Yes? It's very strange because you think that some bang means that something has pushed it up, that is, table has resisted the motion, but suddenly you see the other end going down, and that is what's happening. Now, imagine reversing this process. Let's say you have something like a Japanese karate nunchaku, that is a sequence of rods that are connected by some flexible string and so on, and you start drawing this chain upward. So each chain is on a pile, but when you suddenly draw up, that rod in the middle must spin, and when it spins, it bangs against the pile at the bottom, which gives you, as a recoil, an upward force, and those upward forces build up and then make a chain. You look very suspicious, but here is how you can demonstrate it. My friend at Cornell, Andy Ruina, discovered this wonderful phenomenon a while ago. So what we shall do is to show this movie, but I shall stop it in a moment. Those are two ladders, rope ladders, that are falling, free fall, of course, in slow motion from above. But you'll see that the left one will be stopped by a table. And the right one is very free to fall as deep as it wishes into the abyss. Okay? So the left one will be intercepted by something that resists the fall, and the right one is free to fall. Which one will end up falling faster? The answer, the left one. which is being stopped. So let's start again. Oops. Oh, okay, sorry. So it starts, and look, there is a slight differential, but the left one starts going a little faster. You see? That is very strange. Why is this? And the answer is exactly the same logic. When you see each of those rungs is tilted, so when the first rung hits the ground, it spins, but then pulls down the other side. So it pulls down the entire ladder above, and then when the next one hits the ground, and then pulls, so it tugs from downward, and that's what's accelerating downward this entire thing. Whereas the right one, in free fall, doesn't get accelerated. So here is, ladies and gentlemen, a device for kind of stopping the motion which accelerates that motion. Isn't that strange? Okay. So that's the arena. Oops. Okay. So in Rena's falling ladder, the one that is intercepted ends up falling faster because of the same mechanism. Yes. So crucial in this mechanism is in this trickery is the stiffness of the rod in between. Because if one side is hit and then if it goes frank, then the other side will not do anything. So it has to be stiff. You have to have a very, very interesting local rigidity as part of the body, and that will come back to haunt us in a moment. So chain fountain is this process reversed. So imagine that you run the movie of Rena's falling chain backward. So you start taking up this chain upward, and then you think, oh, that's funny. If I take up from the abyss, it's kind of a normal thing, but if I take up from a table, I have the impression that it's coming up faster than I thought, yes? So something is helping me, and that's exactly the mechanism that I explained. You can do a detailed calculation in terms of those formulas and so forth, and the height to which, in really idealized, sanitized model, height to which the chain rises divided by the depth to which the chain falls is at most 1/2, you can show, and then the fast flow condition which is behind all this is okay if the height to, the depth to which you fall is greater, much greater than radius of curvature at the top. I showed this to Warner and Biggins at Cambridge, and they wrote a very beautiful paper about this eventually. And so, okay. So in chain fountain, what we found was that the reaction, you see, when you learn about action and reaction, okay, action and reaction are equal and opposite in direction, but in this case, action and reaction were kind of equal, but not opposite, but in the same direction. That is very, very anomalous, yes? So this is a special case of a vast class of what you might call anomalous reactions, which may not even be aligned with each other. That is, you can have you can push somebody, and what you imagine that this object will push you back, but anomalous reaction can actually pull you in when you push, or even worse, when you push like this, it can start going the other way, some other way. So let's see some examples of this. Here is an experiment which was done by Hanna Santangelo, became PRL some time ago, and the movie that was taken for me is by Will Steinhardt. This is the son of Paul Steinhardt at the university. So what we are going to see in the movie is this zigzag monolayer of the chain. It's actually the same chain that I have here, and which will be drawn out from the end. So everything is horizontal, and the external stimulus and the arrangement, nothing is vertical at all. So what happens? Let's see. Here is the movie, and when I start, you think, that's fascinating, nothing is happening. But actually, it's 1,000 frames per second, so something is happening. You see, this is being drawn out, and it's being drawn out at a constant rate. Okay, so horizontal draw on the horizontal thing. And you think that nothing is going to happen, but you see, this chain starts sweeping back and forth, of course, and then you see some interesting curly thing that develops, which goes back and forth. And eventually what happens is that it starts standing up, but then it gives up. But then it tries again, now it stands up, and it stands up in a beautiful arch, vertically, although there's no vertical force coming from anywhere. And you see there's a lot of twisting going on at the root of this standing up. There's an arch which sort of snakes back and forth, and it goes on and on and on in a very, very stable configuration. And at the end, you'll see it's very, very cool. When it runs out of the chain, the end snaps and flies into the camera. You'll see. So it keeps going on and on and on. And it stands up. Again, it's a horizontal external force on the horizontal arrangement, and yet the response is vertical. The reaction is not even aligned. It's linearly independent, if you like, of the action. Whew, that's very nice. Yeah, all right. Thank you. That's a kudos to Will Steinhardt. So an arch rises and snaking sideways. That is amazing, isn't it? So how does this work? Well, as the chain is drawing out, this is a bird's eye picture, you see it goes back and forth and it starts collecting the mass of the chain. Okay. So let's focus on 4 points that I labeled A prime, and B prime. But A actually, after pulling a little bit, becomes A prime. Okay. So I pull, and then this solid arrow becomes the dotted arrow. And then B then is called in from far away and becomes B prime. So eventually, A prime, B prime come like this, and then they'll come to the same place. And what happens, at that moment, you have this corner, and you are tugging it in this picture downward. That means that you see in that corner, there is, you should imagine, a miniature rod. Because chain is locally rigid, locally very stiff. I shall come back to that. So if you pull that rod, the rod spins and then pushes, so the B prime pushes out, and then voila, you have a little curvature that forms in a corner. And that is what you saw in the movie too. So what you do is that you go back and forth. This curvature comes back and then collects another curvature. All those curvatures started sort of curling, piling up together. And you should realize that the chain has an unforgivingly singular sort of behavior. And what I mean is as follows. So, not escape, excuse me, not escape. I shall have to do this. Now, I hope you can see this very well. Okay. So, if you want to do this experiment at home, you should have a longish and very thin, delicate chain. But any chain will, in principle, do. A chain is very interesting as an object because, you know, if you want to curve it, it's very happy to be curved, and it just sits there with no resistance whatsoever. It has no stiffness above a certain radius of curvature. But if you want to curve it really tight, can you see? Then there is the smallest radius beyond which you can no longer curve. Otherwise, you'll break the chain. Yeah, this is the smallest. In other words, you can keep curving, and there's absolutely no energy cost. But when you curve too small, suddenly the energy cost becomes infinite. This is a really singular behavior, and that's what explains what lies behind many of these things. So that's, if you like, the stress-strain curve. So as the curvature increases, you know, there's no stiffness, and boom, huge stiffness. Yes? And then it goes to infinity. So eventually, those overcompressed curvatures cannot take it anymore. Yeah? And then when you cannot take it anymore, you get more and more compressed. What happens? Well, maybe the chain breaks, but there is another solution. It's the escape into the third dimension. If you have ambient dimension, you can set yourself free. In other words, those curvatures buckle off as torsion and escapes into. So this is the moment which I filmed where this curvature became sort of curly and stood up. And you saw when this arch was going back and forth how curly the root of the arch was. Yeah? So let's see what you can see. These phenomena prove to be generic. That is, in fact, you don't need much to produce this kind of phenomena. I'm now going to go into the world of metaphors. All you need are shocks, because you have to punch, and really something. And necessarily those shocks are dissipative. You see, when you pick up, you have to go bang, and then it sort of has an upward momentum and so forth. And then also singular stiffness. You saw this strange curve, which you never saw in textbooks of elasticity. And finally, there should be lots of twists and turns which seed those buckling phenomena. So let's see something else. I noticed that at this point that actually we have been very careful in setting up experiments. For example, it takes a long time to do this Santangelo experiment, but I can do much, much better than this, which is I can do it randomly. So I shall now make a pile using this chain. Come on, come on. Oops. And then so this is the chain that came out. And this chain has the property that, it seems to be a random pile, but it is random. But one property that it has is because I made the pile from above, the chain never went down under itself. In other words, when I pull out, it will never get entangled. Okay? So when I start moving this, I don't know if you can see this from that angle. It stands up. So I don't have to actually prepare the experiment. I can do a random configuration. So what happens if you start from a random pile of chains? So I form the random pile, but make sure that this chain pile is random, but it never goes under itself, so that when you draw out, it never gets entangled. It just stands up. And please remark a lot of torsion at the root of the arch, which is exactly where the curvature is buckling off. So now is a good time to show you the really beautiful movie, again by Will Steinhardt. And he was a graduate student at Harvard, and he made those movies for me together. So here is a random chain which is being drawn out. And somebody should set this to music. And you see it starts standing up. And you see those buckling phenomena are very, very common because there are lots of twists and turns which seed the curvature, and then the curvatures accumulate and they can't take it anymore, so they release themselves into torsion in the third space. And you see, it stands up and it just stays there. It's really stable and very, very beautiful. Indian rope trick with a snake going up and so forth. This is the modern version of this. And you see how twisty this is? It starts kind of going down, but it's just going flat. But it's actually going sideways because it's very, very stable. You have fast chain can flow in any configuration whatsoever, as I explained in the 19th century. And then you can stand up again, and it goes on and on. And then at the end, it's also cool. It just snaps into the shape. Yeah. And it's just chain being drawn out of a random pile. There's some beauty in this. And then at the end, whoo! Thank you. So here's an afterthought. So you saw that when the chain started going and formed an arch, either from a regular thing or from the fountain or the random pile, somehow the arch looked the same. It stayed there in space. It didn't sort of go forward or backward and so on. So why does the arch look so stationary? And the answer can be found very easily, and it's a consequence of this formula that I boxed earlier, and I don't want you to remember this, but it's a tension has to be balancing in the fast flowing chain the centrifugal effect, which is rho v squared. You see, this v is a speed, if you like, a material speed at which the chain is moving. So you have some grams of material, and then you have more grams of material over here, and that's the transport. At the same time, according to the elementary theory of elasticity, if you have some disturbance and there's an elastic wave that propagates, and this applies to earthquake waves too, and the speed at which the wave propagates is known to be, in general, square root of elasticity divided by density, by inertia. And in this case, elasticity is T, the tension, divided by inertia, which is rho. And if you look at that, that's exactly according to that formula, well, approximately v, isn't it? Which means that while the chain is moving at speed v, the wave is traveling in this direction at v minus v. So they cancel each other, and so the wave seems to be standing there, stationary. In other words, all waves that you see on this phenomenon are standing waves. That's why it's just there and it doesn't go hither or thither. Okay? So here's the last magic. I don't have to actually do this. So I brought a loop chain here and then a ring. The ring, that's open, but that's neither here nor there. I'm not going to open it, okay, in case you're worried. Now, I put the ring through this and hold it like that. And as you saw, I just put it there. So there's nothing that will stop the ring from falling when I drop it, and indeed it drops. No topology stops it, okay? But now I talk to the ring, saying that, well, they have been very nice at the Institute of Advanced Studies, so maybe you can show something interesting. And then when I drop it next time, what? It got hooked. What happened? There should be no topology. So you know what happened? I don't. This is one of those amazing things which take advantage of everything that we have discussed. So what happened is that when I release, well, the first time I released exactly, very, very carefully. And I trained myself to be able to release and so on. So this is one of those phenomena, magic tricks, where if you are very, very careful and skillful, it doesn't work. But if you are very shoddy and random, it works almost of the time. So the first time the ring fell horizontally, and of course it goes out, straight out. But the second time, I was very careless. And that, you know the first magic, that phenomenon where if you want to release both fingers, one of them actually starts to run away, and the other one becomes a pivot. Well, this pivots, generically, and it starts falling like that, like that, like that, like that. Now, that's okay. You should be able to go out. But at the end, you see, the chain, in order to go out, has to whip around this and then come out. But the chain doesn't want to do this because it has a lot of inertia. So instead of whipping, it slides along this and it gets stuck like that. Yeah. So it's actually an amalgamation of both things, if you like. So what happens is that. Well, that was the last magic for you. But for me, the magic of this occasion was mostly the privilege and pleasure of your company. The Institute for Advanced Study has been such a unique nexus in the history of mathematics and theoretical physics, among other things, that practitioners, you know, of these trades, those fields, tend to think of it as a sort of home away from home, because so many people came to the Institute, and so much science of the 20th and 21st centuries went out of it. Yeah. And yet, for yours truly, shy and always behind the times, this was the very first time that I was graced with an occasion to speak to the people of and around the Institute. This recalls a story. You know, Winston Churchill and George Bernard Shaw were sparring friends. They were always taunting each other. One day, Bernard Shaw sent a letter to Churchill saying, "Dear Churchill, please find enclosed 2 tickets to the premiere of my new play. Come with a friend if you have one." And Churchill replied, "Dear Shaw, previous commitments prevent me from attending the first evening. I shall come to the second evening if there is one." Part of the privilege and pleasure of being brought to a magical place like the Institute for Advanced Study is the occasion it affords of meeting old friends as well as of making new ones. I hope there will be a second time.
Thank you for the wonderful lecture, and I guess it's time for questions. So let me actually start with one. What is the difference between the, I actually don't know the name in English for that gadget. I mean, like, you know, in Italian we call it trottola. So you speak 1,000 languages, so you should understand what I meant. No, trottola is the, you know, the tippy top.
Huh?
So, okay, you said you don't have an explanation for why the other one is chiral, but
This one.
yeah, I mean,
okay.
what is the difference between the two?
I can address this, and provided you don't publish it. No, I'm kidding. So this object was chiral. Yeah, so it's a top, that's a trottola, and 2p, and so on, and the virtual. So this is chiral, and as you saw, it is chiral. I tried it on many surfaces with many people launching with the different initial conditions. It is chiral. Now, chirality might be due to one of the two, many causes, but one possibility is that the surface is somehow chiral. What I mean is, when you learn about friction, many textbooks, elementary courses, treat friction as an isotropic thing. That is, when you slide this way, it's the same friction. But it's actually not in general case. For example, I heard that the Inuits put seal fur under their skis, so that when they ski forward, they can slide very nicely, but when they start skiing backward, the fur breaks. Yeah? So it's an anisotropic, direction-dependent, or the sense-dependent friction. That can happen. So it's in principle possible to imagine that this thing was machined, by the way, this was made accidentally, machined for a special occasion, for that special somebody, but it was so special that I kept it for myself. And it was machined so that in this direction, there's no friction in this direction, but that's not the case. So the explanation must be inside, that is the mass distribution of the body. But, you know, this is a rigid body, well, approximately. And rigid body dynamics is very insensitive to details of mass distribution. Essentially, it cares about two things: where the center of gravity is, and what is the distribution around it. And we professionals talk about the ellipsoid of inertia around the center of gravity. And so you have to position the ellipsoid of inertia in a chiral fashion. And that's actually quite interesting. Anyway, so this is reproducible, so I can, in fact, with MIT, I made some copies of this, and so I can reliably produce this, how to produce this now. But the theory is still, you know, in a few years after my children have grown up a little. And collaborate with me.
Are there any questions? Oh, yeah, back there.
Thank you. It's fascinating. My question, I feel, is very dumb, but I'll ask anyway. You use physics to explain thermodynamics, but what you need to know is that, can you explain thermodynamics itself that gives this phenomenon? That it's in thermodynamics, something in the energy, the conservation law, which somehow it's changed so that we get into second thermodynamics law.
The question was, if I make it a bit more abstract, I seem to be sort of deducing y from x, but can you sort of address x, which is the source of, you know, all those all that information and so forth? But I would like to plead, and that is a very good point, but I would like to plead that that's not what I'm doing. What I'm doing is, in fact, a haphazard way of approaching nature. You see, many of us work within a theory, or direction at least of a theory, so we kind of know what is next and what should fit in, and so on. And that is very important. That's where the major advances in science have often come from. But there is a minority of us who would like to actually look around us in nature and find raw surprises, if I may say so. Surprises in the sense that, you know, I might be an expert in some field, but I look at it, oh, that shouldn't exist, and then, oh, it does. So that's surprise. Because, you see, for me, surprise is really key to progress, at least in this style. I'm not saying that other styles don't exist. In fact, they do in a major way. But the surprise means that before you meet the surprise, you have a certain conception of the universe, if I may be grandiose. But surprise shows that that was slightly wrong, or perhaps in a big way wrong. And after I come to terms with the surprise, I'm ever so slightly but measurably a better person. I'm more intimate with the universe. And that's how I progress. So surprises are very important. So in this approach, all I'm doing is this vast universe with infinitely many mysteries, but then I start making sense. I start making connections. This is connected with this, and that makes sense in terms of this. I'm not actually having a system where there is some kind of axiomatic or starting point X, and then I'm deducing Y. In fact, I'm going back and forth, and I would like to have some cohesion or better intimacy of the entire universe that I can touch and feel and make my own. That is what I'm doing. I'm not doing sort of traditional science in the sense of making a system. And then I can use anything I can use. And eventually, somebody cleverer and more systematically minded than I am will come along and will start making a big sort of grand scheme of things. But that's for other people to do. In the meantime, I'm giving birth to my baby.
Any other question? Oh, here. Sorry, I was not. I'm looking too far away.
We got back there? I can speak loudly. That phenomenon with the chain when it makes shape, does it depend on the speed with this chain is pulled out? If I pull it very slow, I don't think it's going to jump.
Correct. So
if I put it very fast,
the comment was that this phenomenon chain standing up and so forth seems to depend on chain going out very fast. And if you do it really gently, of course, nothing stands up. And that's because of this condition. I'm sorry, it's a bit too small. So look at the boxed formula, and just lying above, it says, while the chain flows fast enough, this happens. This balance happens. Fast enough is rho, that is the density, but it's linear density, mass divided by length of the chain, if you like. And then V is the speed at which the chain is flowing, that's V squared, divided by R. R is the local radius of curvature, if you like, how curvy it is. Should be much larger than the force per unit length of this. It's typically gravity, for example. So you have to have V large enough to win against this external disturbance by quite a lot of margin, and then all of these kind of things can happen for quite a long time. That's why you need V to be large. You can't do it too slowly.
That is one extreme. If I pull it very fast.
Yes?
Extremely fast.
Yes.
What happens?
Oh, extremely fast. Within reason, this becomes better and better. But if you pull it so fast that it is faster than the speed of sound in the chain, then the chain starts breaking.
It won't behave like this.
No, this chain will start breaking as material because you are pulling too fast, because there's too much shock.
No.
Then within reason, so you and I are very reasonable people. I was thinking about some colleagues of mine. And then this becomes better and better. It becomes really, really pronounced.
And how high is the fountain?
Oh, so that's kind of the sanitized model, which is that in some kind of idealized limit, the height to which the fountain, for example, rises, as a function of the depth which it has fallen by that time, is about 1/2. It's at most 1/2. It can't go up higher than that. And this is assuming lots and lots of things are cooperating. And in fact, in practice, it turns out to be something like 1/8 or 1/10. So it's nowhere near the limit.
Okay, we have another question from a small participant in the audience. Yeah, a young one, sure.
She's a little shy. She wanted to ask for a second to explain again why the ring got stuck.
Why did? Sorry?
Why the ring got stuck.
Why the ring got stuck?
Ring got stuck.
The ring.
Ring got entangled. Thank you very much for bringing that. So why does this work? Well, first of all, you should go home and try it. Well, it's actually not so easy because you should have a fairly soft chain like this. I bought this from Kankayuri, how to say that, hardware store near Harvard Square, and I had only $3 in my pocket, and that's why it's this long. And in fact, if I had much more money in cash, I would have bought one. Anyway, so and you use a ring, and the ring, it's best if the ring is quite heavy or dense. And then when I drop it, well, it doesn't work. But then if I drop the second time, and it works. So what happens is you should begin by sort of going home and trying to sort of hook this chain or something like a loop onto a ring like this. So you might think that, well, in general, you have to sort of open this thing and then put it in and then do that. But that's really linked. Yes? But there's another way of linking it, which is not quite linking it. You can put it like this. And maybe I should show it on the movie. And that's actually very useful as a practical skill. And you know, sailors do this all the time. And okay, so here, okay, and a little further in, further out. Good. So you put this chain like that, okay? And what am I doing actually? And then if you go out and like this, do you see? So the chain is coming in, goes out and then goes under. Is that okay? And when I pull, oops, wait a minute, so what is going on? So I should do that, and then it slides, and then I think, yes, this works. And then when I pull, it hooks like that. So I don't know if you can see the final configuration, and then maybe the mummy can help it. Okay, so I'm going to lift it, Derek. So do you see what's going on? So excuse me, maybe it's not so clear. I'm going to look it. Maybe this is best. Okay, so the chain comes in and then goes under and over, and then you see, and you can actually unhook it like this. It doesn't. But if you put it like that and then pull, it gets entangled. This is what's happening in a flash at the end. And that's happening in a flash because what's the incentive? Because the chain has inertia and it has local stiffness. It doesn't want to curve too much and be whipped around. It wants to sort of keep some straightness, and that's why it prefers to slide and hook rather than to whip around and then get out. It's really best. So why don't you come and play with it? I'll show it to you really hand to hand.
Okay, maybe we take another quick question. Oh, there's actually two. Yeah. Yeah, the gentleman over there.
Do these tricks work with a rope or a string? Because you use a chain in all your tricks.
That's right. The question is, does this phenomenon occur with ropes or string? And the answer is no. And the no because one of the ingredients of this really necessary ingredients, almost sufficient ingredients of this class of experiments, is among the three that are listed in the top right corner. So you need shocks, and you need singular stiffness, and that's the thing, and twist and turns. So singular stiffness means that in the case of a chain, when you sort of try to bend it, it shows no resistance. But when you try to bend it too much, it shows infinite resistance. You cannot curve it more than a certain radius of curvature. Whereas with strings, you can almost flatten it. Yeah? So the resistance is really weak, and that spoils the effect. A rope is very interesting. Usually it doesn't work, but I have seen actually in Boston Harbor some rope that has been tossed in and it stood up a little bit. So it's not so clean because of various other circumstances. And that has to do with actually shocks. The rope is too soft, and so the shocks are absorbed and so forth. The chain is really wonderful.
We maybe take one last question. So there's a young gentleman over there who raised a hand. Yeah. Yes, over there. Yes.
Seems that my thought matches exactly with the last audience. I was just about to ask whether this phenomenon will occur in ropes or like infinitely small chains.
So I would like to then give a different answer. You see, and this really has to do with what I wanted to get across, which is that I really wanted to find surprises, however modest, your individual surprises, personal surprises, and surprises that make us slightly better, slightly more intimately with the universe. So, yes, I'm telling you all this, professorial type, maybe an old man, and this sort of with a loud voice and so forth. Those are authorities, but ultimately, when you ask a question, like when you wonder about, well, does it work with a string, you have as much access to nature as I do. You don't have to listen to me. You can try it yourself and you can find out. And then it's your universe now. You can make it your own. So can you have the microphone a little closer?
Sorry. Could you please go back to the slide where you explain how like a rigid body rotates while it hits the next chain? Yeah, I think, yeah, this part. So how I thought about this question is that when you make the like a single part of the chain smaller, when you rotate it, like it will produce less shock to the next.
So excuse me, I'm going to interrupt you because I think people want to go home. But I answer. So the question I think is, look, this seems to be a very discretized model of rods that are connected and so on. But the chain, has very, very small sort of rings and so forth. And if you take the limit, what happens? Actually, it turns out that in this, I didn't write down the theory about this, but you can. And in fact, that's the theory from which those estimates come. In fact, the length scale of the chain, which you put in, so length, let's say L of the rod, actually disappears from the equation. A little bit like in the sort of flowing chain phenomenon, the radius of curvature, that is geometry, disappears. So, because the length scale is no longer there, you can take the limit as the length scale becomes 0, and the theory works fine. So it is actually a theory that works for the continuum, for continuum mechanics as well. So you don't have to have this. Yes, but it's a little less convincing. It goes a little higher because, as I explained, the rope is a little softer. It absorbs the shock too well. It's too. Okay. Good.